All right, so let's get started. Hello, namaste, and welcome everyone. Welcome to this problem solving session. Uh, Today's tutorial problem solving session is going to be on sequential modeling of data, and or more correctly, it will be on how we deal with uh, in deep learning. What is the deep learning way of dealing with sequential data? So another note for people who might join later is that I have some urgent work around 7:15, 7:30. So I will try to wrap this around quickly. In case you have some doubt from this session, then maybe we can take it up in the next solving session. Uh, so by keeping that in mind, let's get started. So this is week 11, all right, and it is on uh it is mostly on sequential data. Or if I have to be, if I can be a bit pedantic, it is on how to handle sequential data. Right. So all right, so this is going to be the this was the broad theme of this week's topic, uh, week 11 content of week 11. So so basically, I mean, this is what we have been building up to. So if you remember, we initially we were dealing mostly with feed forward networks, right? Feed forward networks. Then we sort of shifted gears and saw that okay, what how can we deal with images? How can we deal with places where the input has some sort of spatial structure in it, right? So to deal with those kind of data, in particular to deal with CNNs, to deal with images, we came across something like convolutional neural networks. Convolutional neural networks. Right? And similarly, this week's focus is going to be on recurrent neural networks. Recurrent neural networks. So, I mean, I so these are all big terms and big names and stuff. But I hope that you are able to appreciate the fact that these are all just design choices in some sense, right? I mean, so end of the day, what is happening is just back propagation. You are defining some loss, and you are back propagating, and you are updating your parameters, and something like that is going on. However, the difference amongst these between these paradigms come because we are sort of dealing with different kind of input data, right? I mean, if to give you some something which is not there in this course, in real life example, I mean, it is possible that you deal with something which is not either an image or a sequence or a vector. Okay, it is possible that you can deal with something which is very weird. For example, you might deal with something known as graphs, right? So for example, I mean, if you use Facebook or Instagram or any social media app, you get suggestions, right? That okay, this is some guy. So Facebook will tell you that okay, this is some guy that is there on Facebook. You might want to be a friend with him or something like that, right? So that kind of uh, 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 recommendation comes out. So the modeling uh, which goes behind such models is the data that goes behind such models is actually modeled using graphs, right? Or even some dating apps that people use generally, right? So you so they get some recommendations from you, and then they suggest more recommendations, right? So these kind of suggestions come based on, they consider each person as a node, and let's say you give some feedback, and based on that feedback they establish some edges, and so it becomes a graph eventually, and that graph is used to give you more recommendations and stuff like that. So I hope you can see that graph is even tougher, in some sense it is even more tough to deal with graphs. But nowadays we have something called graph neural networks. So I mean, so like even in graph neural networks and stuff like that, right? All we do is define some laws, define some architecture and stuff like that, and use the laws to back propagate and update the parameters. So the broad theme that I want to convey here is that all of these things might look very weird, at first glance, but end of the day, the underlying principles are, very similar. And all you are doing is, you're defining some loss function, you're back propagating, you're updating your parameters, and nothing more than that. Or I mean, the difference that comes between these paradigms is just because we are dealing with different kind of data. I mean, in some cases we are dealing with vectors, some images, in some cases we are dealing with sequences and stuff like that. So I hope you are able to see that. And I mean, that is the reason, why one should not get intimidated with these big terms and stuff like that. Okay. All right. So as I told, I am in a bit of hurry today, so I will try to finish this tutorial bit early. I have to be somewhere. Nonetheless, I will try to solve all the problems, and give some brief overview. So I won't go into details like I did in my previous problem solving sessions, but maybe I will see what I can do. Okay. All right. So to start with, so the broad theme of this entire week has been something called something called recurrent neural networks, right? So okay. I mean, so what does recurrent mean? I mean, I hope the English meaning of recurrent is that something is happening again and again. So if something is recurrent, you that something is happening again and again. Okay, so these are some questions that you want me to solve. So sure, I will solve these questions first. 4, 6, and 8. All right, I will do that. Thanks for making that explicit. Okay, so the I was saying that the English meaning of recurrent is that uh, something that occurs again and again. So, for example, so one example of something which is recurrent is this lecture itself, right? So every week we are having this lecture. So one can say that this meeting or these lectures are, recurrent. So, so that is the English meaning of recurrent. However, what does this mean in our context? So, as I said earlier, we are trying to deal with sequential data, right? So sequential data means, what does a sequential data mean? That data is coming in, that the data is coming in some sequence. Okay. For example, so let's say that let's say there are different timestamps. Okay. So let's say at first timestamp you got some data x1. At second timestamp you got some data x2. At third timestamp you got some data x3, and similarly at tth timestamp you are getting some data xt, and eventually there were, let's say, there were n timestamps, and the last data that you received was xn. So this is a sequential data, right? What makes a sequential data different from a general vector input? Well, the main, and of course the main difference is that there is some, you know uh, there is some correlation. So there is some correlation So these inputs are correlated. Okay, what do I mean by correlated? So specifically I mean that x3 and x2 are not independent. Okay, x3 and x2 are related. Xt and x1 are related and stuff like that. So this is what we mean by correlated data, right? And another thing to note here is that each xt, so t is the subscript that I'm using, which denotes the timestamp. Each xt here belongs to, let's say, some rd, right? Or maybe let me use rn. Okay. So in a general neural network, each input was what let's say uh, each input was, let's say, of dimension rn. However, this is one input. This in the case of sequential modeling and sequential data, this is my input. So this sequence is my input, right? And so maybe okay, let me change this to rm. So I hope you can see that my input. So input dimension here, what will it be? It's not just Rn, it's Rn, and there are m such inputs. So it's Rn cross m, right? So it's like a matrix or something. That is how the inputs are. That is the dimension of input. All right. So this is a sequential data, and the way to deal with this is using RNNs. So how do RNNs deal with it? So the idea is to get, so of course, I mean, as you must have thought of this immediately, that the one obvious problem that one will run into in these settings is that we don't know the value of m. So m here is unknown. For example, if the input is a sentence, I don't know how long the sentence is going to be, of course, right? So so how does one deal with such problems where the so just to make it very explicit, if m is unknown, what does this mean? So this thing means that input dimension is unknown, right? Because I hope you can see that there is an m here in the input dimension, and m is itself is unknown to us, right? So this is a big problem that we are going to run in. So so to avoid this problem, this is where the meaning of recurrent that we were discussing comes into play, right? What we do what we do actually is the following. Okay, so let's say you have a stream of data x1, x2, and something like that. You are getting some xt, some xn. Okay, the idea is that I don't know the length of this sequence, right? So I will say, okay, that's all right. However, I do, so there is something that I do know, right? I know what is the dimension of these individual inputs, right? Because this is up to me. Why is this up to me? Remember, we have learned how to compute embeddings of words and stuff like that in one of the previous weeks. So representations such as bag of words, glove, and stuff like that. So from there I can I can come up with a dimension that I want to use, and that dimension I can fix for all of these inputs, right? So that is a good thing for me. Now, so the question is, can I exploit this? Well, so people earlier people came with weird techniques, and so there were some deep belief networks, and maybe if you want to go into history, you can read about Boltzmann machines and stuff like that. But the thing is, they were very inefficient. Uh, so you know, uh, since it is yeah, so I mean, I don't want to go into those historical context. Maybe it will be we will diverge a lot. So without wasting time, there were, so the point is, there were a lot of redundant ideas, not redundant, but maybe primitive ideas that came before RNNs, which were not good enough, because of which we don't use them anymore. However, what did RNNs do? The question is, what did RNNs do? So RNNs are, a clever strategy to deal with such things. So what is the idea? The idea is that, okay, there is some model M, let us say that there is some model M. Okay. Now, so M is a parametric model. I mean, it can be a neural network or something like that, right? I mean, that is something that I can model basically. The idea is I will use the same model again and again. Okay. The same model will be used again and again. And let's say if the problem is, many to many, so at each time instant I will take some input, I will predict some output, something like this. So this might be y1 hat, this might be y2 hat, yt hat, and something like yn hat. Okay? It's something like this. So this is a possible. So so the idea is that instead of making my model dependent on the size of input, what I will do is I will use the same model again and again. Okay, this is the idea. However, this thing, doesn't make any sense. I mean, this thing that I have shown here, this model here that I have shown, doesn't make any sense. Why? Well, because this is not taking into account the correlation that we just discussed here, right? I mean, we know that x1 and x2 are dependent on each other. I mean, there is some relation between them. Xt and x1 are related, and xm and x2 are related, and stuff like that. This model in this current form doesn't take that into account. Okay. Okay. Why doesn't? So why is it not good? Because it doesn't take into account. Why is it not taking that into account? Is because it is treating x1 as individual input, I mean independent input, and it is saying that okay, y1 hat is the output. X2, it is treating X2 as an independent input and Y2 hat is the independent output. However, it is not taking into account that X2 and X1 are also somehow related. I want that inductive bias to be accommodated into this network. So a simple way to circumvent that is that, well, okay, what I will do is I will define another parameter, let's say some W, which will connect this block across different time steps, right? So so maybe m1, so this model, and let's say this is state like time step 1, right? And this model is here at time step 2. So this is the same model. However, the model is designed in such a way that it will take into account whatever some information from the previous state by using this parameter w, right? So this is a brief idea that that recurrent neural network uses. So this same pattern continues. So at this at time step m, it will take some input from the previous block. Okay, it will predict some output, and the information of this block will be passed on to the successive block using again this same parameter w, and same thing will go on till the terminal time step. Okay, so in the this is what is the gist of recurrent neural network, right? So let us think about it. Have we circumvented the problem of unknown? Okay, sorry. So I was saying that, so let us think about it. Have we circumvented this issue of uh, you know multiple time steps, unknown timestamp to deal with this sequential data? Well, the answer is yes, right? I mean, so well, my model now is so eventually my model is just taking two inputs at any time instant. Okay, it is taking only two inputs. What are those inputs? One input is from the previous block, so this you can consider as one input, and it is going here. Okay, and the other input is the current time step input. Okay, the so the input at that particular times instant is also one input, right? So these are the two inputs that are going in one model, right? So so I have reduced my problem of modeling this m the sequence of length m to just modeling two inputs, one input from the previous block and one input from the current time instant. time instant, right? So this is the, brief overview of how we are dealing with uh, neural networks, so sequential data, right? All right. Having said that, next thing that I will just explain. I mean, I won't go into detail, but I will just explain. How do we work with these things? So as I mentioned, these are I didn't I haven't specified what these individual models are, right? But so these models, as I hinted earlier, are nothing but just neural networks, simple neural networks that we are very comfortable to work. We are very comfortable in working with neural networks, right? Okay, so each block M, how does it look like? So this M, it has some form like this, right? So what it is doing is, so so let's say that there is some hidden layer, okay? Some, let's say, so I am writing this in general. So this is the general model. So this is, let's say, H, okay? So there are two inputs to this model, right? One is what? One is some Xi, right? This is a vector, I know, because as I just discussed that these are nothing but word embeddings that we have discussed in one of our previous lectures, right? So Xi is one of the inputs. Okay, what is the another input? The another input is maybe something called hi minus 1. Where is this hi minus 1 coming from? Hi minus, so if, so let's say this is my current block, so this might be H, okay? This previous models hidden layer, okay? This previous models hidden layer is also taken as input, which I'm denoting by hi minus 1, right? So let me call this hi, okay, to make it explicit. So what I'm saying is that the current hidden layer of the neural network takes two inputs. One is the current input at the current timestamp xi, and the other input is the hidden state from the previous time instant, which is hi minus one. Okay, this is okay. So how do we calculate hi? It takes, so hi minus 1 is multiplied by a matrix W, all right? Xi minus 1 is multiplied by another matrix which is U, okay? Something like this. And then we can output, whatever my output is, let's say some Y. So let's say yi hat by multiplying hi with some another matrix B, right? So this is how, this is a simple way to uh, model the model the sequential data. So if I have to, maybe if I have to represent this figure in this form, it will look something like this. That you have hi, okay. So this is my hi, right? So this is my hi minus one, hi minus one, and there is some input which is xi, okay. Some xi is also there. We are using this and this is being multiplied by w, this is being multiplied by u. There is some operation that we will do. I'm not saying what that information is, and that will give me hi as output, okay. Just maybe I will take this, okay. Okay, so right, so this gives me hi. Now what we do with hi is, I multiply it with another vector b, another matrix b, to get some output which is, let's say yi hat, something like this. So it's a very simple model, right? And just to remember that this hi will also go as input, in the next uh, time instant, which will, where we will again multiply this by w. Okay, okay. So this is how so I hope you can see, that this model, and so this you can look at this as a detailed version of this model what we were discussing. So how, so now to be, just to be specific, what are these HIs, how are these HIs, and things calculated? Well, each HI, so maybe I will draw this line there, and uh, some other color. So each HI it is calculated in the following way. You will use some activation function sigma. So this xi is multiplied by u, right? So u times xi, okay. Then hi minus 1 is multiplied by w. So w, so we will just add the two things, w times hi minus 1, right? Plus some bias term b, just like simple neural networks. So this will give my, so this operation will, so this is sigma, so this is your sigma operation that I was talking about. Okay. Okay. So and how is yi hat computed? Well, yi hat is computed, in a similar fashion, which is, you apply some activation function, let's say O, to v times hi, right? So hi is multiplied by v, and plus some bias term c. So this is how you will calculate, right? And just to note, what are the parameters that you would like to learn? U is one parameter, right? W is another parameter. V is another parameter. B is another bias parameter. C is also another bias parameter, right? So this is, a simple recurrent neural network that we use in practice to deal with sequential data. All right. So maybe so we are 28 minutes. Uh, so we so, okay, so 28 minutes are over. So let me just explain. The problem of vanishing gradients in brief. Okay, because that is some problem that we deal with RNNs. And after that, I will start the questions that you are mentioning in the chat box. Okay. So for the new joiners who have just joined, maybe if you wish me to solve some problem, just maybe put it down and I will solve that question. Okay, because I have some commitments today and I might have to leave early. So please, if there is some problem that you felt is very tough, was very tough, and you didn't understand, maybe you can jot that down. All right. Okay. So having said this, okay. So let me come to the problem of what is called as vanishing gradient, right? So the problem of vanishing gradient is as follows, right? So okay, maybe I will copy this thing. Uh, Let me copy this thing. Okay. Uh, yeah. So maybe we will make it here. So this is vanishing gradient. Okay. So as I earlier said that uh, even though this thing looks big and very weird and maybe might be intimidating at first, it is a very simple thing. End of the day, we are going to calculate some loss, okay, and then we are going to backprop that loss to learn the parameters. That is, I mean, that is the soul of neural networks and deep learning in general. So once you are comfortable with that, nothing will intimidate you. It's very simple. Okay, so having said that, let us talk about the loss function, right? So so let's say, I mean, this is the general case. Let us say that there was some, you had some ground truths. So this is a supervised setting. You have the labels. So y1 hat is your predicted output. However, you had some correct output at your hand. I mean, you knew what the actual output should be. So that is y1, y2, yt, and ym in general. Okay, right? So the this letters in green are the actual outputs, whereas these letters in blue are the predicted output. So using these two things, I hope you will agree that I can calculate my loss function, right? So let's say this is the loss function L1 at time instant 1. This is the loss function L2 at time instant 2. This is the general loss at time instant t. I will get some loss LT. Similarly, Lm, right? Okay. Now my overall loss function. So the overall loss L, what will that be? I hope you will agree that if I have multiple objectives L1, L2, LT, and LM, I want to reduce all of them, right? So if I want to reduce all of them, all I have to do is if I reduce the sum of them, right? If I reduce the sum of LIs, I will eventually be reducing L1, L2, Ln individually as well, right? So my what will be my overall loss function? It will be L1 plus L2 some LT plus LLM. What will this become? So this is nothing but summation Li, right? Where I is going from 1 to some M, right? Or so so I hope this was clear, right? There's not nothing much to look here, right? Okay, so let me go one step ahead, right? What will this loss function look like? This will be I equal to 1 to m. Some loss function, some loss function. So let me denote it by small l. Yeah, okay, L of what? L of yi hat and yi, right? This is how it would look like. Right? Okay. Now, what is my yi hat? Okay, this is okay. Make this summation explicit. We don't want to forget that there is a summation L of. So let us see what yi hat looked like. This was something, right? Yi hat looked something like this. Well, let me see. This is O of Vhi plus C, right? Vhi plus C, comma yi, right? This is how it was looking like, right? So this is good, right? Let's see. Let's say if I want to calculate del L by del what? Del L by del V. Let's start with, if you start, so this is where the loss will be calculated. So maybe if you want to go back, the first thing that you will encounter is V, right? How will that look like? So that will be del of L of O times B Hi plus C, comma Yi, right? Something like this by del V, right? Okay. What will this? So by using the regular chain rule, or simple chain rule that we have been using till now, what will this become? This will become del L by del of O V Hi plus C, comma Yi, yeah, by what I will do is I will take del of O V Hi plus C, right? So I'm using this argument as first thing into del of O of Vhi plus C, comma, okay, sorry, just this thing by del V. Now you can see that O is known to me, right? So O is known to me. So it will be something like logistic function, or whatever, can be softmax or something like that. So I can always calculate this, and this is also calculatable because the loss function is also known to me because I have designed that loss function. So this is also computable. So this term and this term, both of them are computable. So there is no worry. I can simply use this thing, right, to calculate the loss function. So what will it become? So I hope you will agree that so if I so taking this from here, right, del L by del V will be nothing but summation of I equal 1 to some M. What is this? Del by del V of L of O times Vhi plus C, comma Y. Right? So this is what it will be eventually. So nothing great, right? I mean, it was very simple. However, the problem will come when you start differentiating with W's, right? So okay, so 1 plus 1, right? So the problem you will encounter is when you start with dealing with W's, okay? So by this similar analogy, I hope you will agree that del L by del W will be nothing but summation I equal to 1 to m del by del v, okay, del by del w, sorry, I'm really sorry, del by del w of L of O times VHI, O of VHI plus C, comma yi, right? Well, now what is the issue? Why is this non-trivial? So let us look at this one of these terms, right? Okay, let us, so instead of, I will consider the summation later, but let us consider this thing first, okay? All right, so del by del W of L of O times VHI plus C, comma yi. Why is this difficult to calculate? Well, this is difficult to calculate because it is recursive. Okay, what do I mean by recursive, right? Okay, let us see. So let us look at this thing, right? This thing. So let us now open our minds, right? So I have some yi, yi hat and yi combined to make some loss function f. Okay, maybe I can use some color here. Use color yi hat, and I also have yi. Both of these will combine to calculate some small l, right? Now, if I want to calculate the gradient of this thing L with respect to W, let us see what happens. Right. So I will have to compute the differentiation of this with respect. So where is W coming in? Yi hat is dependent on W through Hi, right? Hi depends on W, right? This is what this is where the W is coming. So Hi depends on W and Yi hat depends on Hi. So that is how we are going to come across W. However, this is not the only place where the loss will be affected by W. Other place where it will be affected by is Hi minus 1. Now see, Hi is dependent on W. Similarly, Hi minus 1 will also be dependent on W, right? Hi minus 1 will also have some similar formula, right? Sigma of U xi minus 1 plus W times Hi minus 2 plus B. Something like this will be there. So Hi minus 1 also has, so Hi minus 1 also has some component of W, and this W is already there, right? So this is where, we start facing problem. So let us see, I mean, so if I have to write it down here, what will this become? This will be del by del L of O of V Hi plus C, comma yi by del of O of, let's say, VHI plus C. Okay, this is the first term into del of O of VHI plus C. I hope you will agree that I will have to take del by del HI, right? That means by using chain rule. Now I have to multiply del HI by del W, right? This is what I will have to do. Well, now this is tricky now, right? Because del Hi by del W will have a term of W in it. Right? Let me show you how. So what we saw was Hi was equal to some sigma times sigmoid of W. So it was U xi plus W times Hi minus 1, right? Plus some bias term B. I just remember this was how it was, right? So this term will now further become what? So so I hope that I have to differentiate this with respect to W, right? So this will become del Hi by what? Uh, just to just to be safe, uh, just remember that everything is good. Okay, right. So this will how it will become. So I will have to take uh, right. So basically I will have to use. So let me just write. So I will explicitly write this down. Uxi plus W times Hi minus 1 plus B, differentiation with this with respect to W. So since there are two terms that are dependent on W, right? I hope you will agree that I will have to do something like this. This will become del by del W, right? Plus, so in for this, I will keep Hi minus 1 constant, right? I am just using, differentiation of multiplication of two functions, right? And then I will have to take del of uxi plus w hi minus 1 plus b by del hi minus 1. Okay. Just create some space for myself. Into del hi minus 1 by del w. Something like this will come up. I mean, I'm just using the simple chain rule that we have been using, and so I have done nothing. So if you are wondering how did this come from, so I have used something like this, right? So let's say I have to do del by del x of f of x times g of x, right? So what we do is you do f dash times g plus g times f dash, right? This is sorry. So this will be f times g dash, right? So this is how you do it, right? The differentiation of multiplication of two functions. So that is what I have done. So the first time I am differentiating it with respect to just this w, right? This is that is this term hi minus 1 is kept constant here, and next time I am differentiating it with respect to del hi minus 1, and that will decompose in these two terms using same rules. Right? But however, we are not done yet. I mean, there is still something that we will have to deal with. What is that thing? Well, now, so this was del hi by del w, right? Similarly, del hi minus 1 by del w will also have a sequence, that will go beyond it. So it will have del hi minus 2 term, and I hope you can see that, there is a recursion that is involved. So it's like something like this, right? So to calculate hi, you had to go to hi minus 1, which was again dependent on w. And now to calculate gradients of hi minus 1 with respect to w, you will have to go to hi minus 2. And similarly, something like this will go. So this is where recursion comes in, kicks in, right? So I mean, so the I think the general formula looks something like this thing, right? Del hi by del w plus you have to do del hi by del hi minus 1. Okay, and then you have to do del hi minus 1 by del w plus del hi minus 1 by del hi minus 2 times del hi minus okay, so I think I missed one part, right? So this will become del hi by del hi minus 1 times del hi minus 1 by del hi minus 2, and then you have to do del hi minus 2 with respect to del w. Similarly, this thing will go on. So this will go on, and eventually you will get some term like this. Del hi by del hi minus 1, del hi minus 1 by del hi minus 2, I minus 2, and you will do this products, and there will the last term of this product will be del hi minus, so I think it will be del h1, right? Del h1 by del w, something like this. So this will be the last term, something like this will be there, right? So I mean, I think I took too long to explain this. I mean, I hope you have seen the lectures, and maybe if I was not so clear, maybe you can go back and see the lectures, but this is the gist of it, that these things are recursive. You have to calculate the previous activations to calculate the current activation, and hence it's not so straightforward. This is what it is. Okay, now look at this thing, right? This thing is very, so this is something which worries us. Why? Well, this worries us because of the fact that uh, each of these activations will be like sigma dash. I mean, it will be like differentiation of some activation function, right? Something like this will also be sigma dash. This will also be some sigma dash, and something like this will be there. And the problems with certain activation functions, like if sigmoid is the sigma is your logistic function, let's say, then sigma dash is bounded by is less than or equal to some 1 by 4. Okay, this is something that you can prove. Then basically what you are doing is, let's say this is some 1 by 4. Let's assume that all of them are 1 by 4, right? That is the maximum value that each of these term can take. So this will be 1 by 4, right? So similar multiplication till 1 by 4. So what will this become? So it will become some 1 by 4 to the power what? Some I, right? And let's say my I is, let's say if I is equal to 10, this term will, very close to 0. So which means that, in some sense, these gradients, this gradient is not conveying anything. This gradient is not conveying anything, and something like that is happening. So this is what is happening, right? So your gradients, so the gradients that you are calculating are going to 0. So this is what we call as, vanishing gradient. Okay. This is like the general phenomenon that we refer to as vanishing gradients, and I think vanishing gradients is something that we had also discussed in one of the previous weeks. I don't remember the exact date, but yeah, I think we have already seen this. This is just another instance, where we are again seeing. Okay, so this is vanishing gradient. So this, I think, these are just the major topics that, are focus of this week. And like there is another topic, to tackle with vanishing gradients. We go to other architecture, which is called something called LSTM, right? And LSTM tries to, get above this vanishing gradient problem by using, gates, forget gates, right, and something like that. Uh, so I won't explain that because it's very simple and I think you can see it. Okay, but nonetheless, this is the, gist of this week's lecture. If you understand RNN, I think it's more than enough. I mean, you can always go ahead and, see how LSTMs are working, what are each of the gradients and stuff like that. But that will be, too much. And after one point, because deep learning models keep getting bigger and bigger, it will become very difficult to keep track of, each of these gradients, what the gradients are, what are the closed form expressions for each of them and stuff like that. So after one point, you will have to, take some leap of faith and, just say that, okay, this is my architecture and I will just back up and stuff. Okay. So after this, I will solve the problems that you have been mentioning in the chat box. If there is some doubt related to these topics, or I mean, if I was not clear at some instance, maybe I lost you. You can let me know. I can explain those doubts. So yeah, so please ask questions if you have any. All right. Otherwise, I will start solving the questions that have been mentioned. All right. All right. So the questions that have been mentioned are the following. So question number. Okay. So the questions are the third question. 4, 6, and 8. 4, 6, and 8. Okay. These are the questions that I will solve. Thank you. If there are no doubts, I will start solving these problems. Okay. All right. So let's start with the third question. Third question, for the third question, we have some data that is being given to us, right? So we are said that okay, this figure is not very clear. Okay. Okay. So we are there is some. So I will just take this figure from here. Okay. I will just take this figure and copy it. So copy this. Paste it here. So this is some network that is given to us, alright? And what are we said is that we have said that each of the model architecture is something like this, right? So it takes two inputs, x1 and x2. It has three hidden layers in the sorry, there are three neurons in the first hidden layer, right? Something like this is there, and there are two output neurons. So this is what it is. So this is h1, this is h2, this is h3. This is y1 hat, and this is y2 hat, right? Okay. So the third question is saying, what is the dimension of parameter matrix W which connects states in RNA? So we are being asked that, as I just discussed, this is the weight matrix that connects the two models, okay, from the previous state and the current state. Okay, so let us see. So the first thing to, compute the dimension of any matrix is what are the two inputs, what is the input of the given. So I hope you will agree that what we are going to do is W times HI minus 1, right? To to compute the, and I mean, so like, s- let's say that this is what HI is. I mean, the dimensions won't change, so this is, let's say, what HI is. To to compute the weight, we should know what is the dimension of the what is the input matrix, which is HI minus 1, and what is the output matrix, which is HI. And for that, like, to compute the dimension, we need to know what is the dimension of these two inputs, okay, these two quantities. So I hope you will see that since my HI vector here is, is three dimensions, it is three dimensional because it has three neurons, right? So I hope that, HI will look something like this, right? So H1, H2, H3. So these are the three neurons, right? And at time step I, right? This is what this will look like. And similarly, HI minus 1 will be something like H1, H2, H3 at time instant I minus 1, right? Something like this. Now I have to multiply this matrix, which is R3, sorry, R, R3 cross 1. I have to multiply this matrix with, this vector Hi minus 1 with some matrix W to give Hi, which again has a dimension of R3 cross 1, right? So this is R3 cross 1. This is R3 cross 1. What should be the dimension of this matrix, right? This is the question. This is the question. R what? Okay, so n cross m, something like this, right? Something like this. So the first thing is that to be, if I want this vector matrix multiplication to happen, this 3 and this m should be equal, right? I mean, the number of columns of a matrix should be equal to the size of the vector that I'm multiplying it with. Otherwise, the matrix multiplication can never happen. Okay. So, so I hope that you know this by, basic algebra. So m is going to be 3 for sure. Okay. Now, if m is 3, right, what will be the dimension of the this vector that we will get? It will be r n cross 1, right? So this 3, so this, let me just- so this is, so the weight matrix W is n cross 3, right? And Hi minus 1 is 3 cross 1. If I multiply these two, this dimension gets collapsed and it will become n cross 1, right? And now I know that, n cross 1 has to be, this thing has to be equal to 3 cross 1. So this means that n has to be equal to 3, right? So from this, what I can say is that, W should belong to R 3 cross 3. So it should be a 3 cross 3 matrix. That will be the dimension of the matrix. If there is some doubt, you can unmute yourself and ask questions. If I was not clear, or, if you didn't understand something. Okay. All right, so this was the third question. What is so okay? So let me just cut off things that I have done. Third is the question number 4. Okay. Uh, so this is the fourth question. The fourth question is saying that we are given an RNN with the norm of the matrix W equal to 3.5, right? Okay, good. The activation function that we are using, that sigmoid, is logistic, right? Okay, and they have defined some quantity nebula, which is norm of del S20 by del S1. So S is, I think, the equivalent notation for H that I have been using, S20 by del H1, right? Something like this. So this is what they're saying. Okay. So okay, so let's see what this quantity will look like, right? Okay. So del H20 by del H1. I hope from this discussion that we had with, with this computation of this big matrix. I hope you will agree that, so I think it's for del h2 by del h1 should be here. So it is asking us for the this first term, like except the last term, what is the multiplication of the rest of the terms, right? So something like that is happening. So I hope you will agree that I can write this as del h20 by del h19, right? Into del h19 by del h18 into del h18 by del h17, and similarly I will go till del h3 by del h2 into del, sorry, multiplication del h2 by del h1, right? This is how it will be. So I, by using chain rule, simple chain rule. Why am I able to write this? Well, remember that your h20 looks something like this, sigmoid of what u times x20 plus w times h19 plus b, right? If I have to take the differentiation of this with respect to h1, how is this? So how is h20 related to h1? Well, h20 is related to h19, right? H19 will be related to H18 in a similar fashion. H18 will be related to H17, and similarly, we will have some relation between H20 and H1. So just keep this in the back of your mind when you are solving this. Okay, right. Having said that, so maybe I will just take this down. So now we are also given that we are using logistic function. So each of these things will be nothing but sigmoid differentiation of a logistic function, right? Sigma. This will be sigma dash, sigma dash, sigma dash. Again, this will also be sigma dash. This will also be sigma dash. I mean, this will have some form, but eventually it is just a differentiation of logistic. And as I just discussed, each of these logistics are upper bounded by 1 by 4, right? So 1 by 4 times 1 by 4 times 1 by 4 will 1 by 2, 1 by 4, right? So how many terms are there? Each of these term will, so I think there are what we are going on 22. So there are I think 19 terms, right? 1 by 4 to the power 19. Now 1 by 4 to the, what can we say about 1 by 4 to the power 19, right? This is what 0.25 to the power 19, right? So this is like a very small quantity, right? So 0.25 is already very small, and now we are like, I hope you will so, or other another way to say it is that this thing will be 1 by 4 raised to 90, right? So 4 raised to 19 is like a very big number, right? 4 raised to 19 is what, if you want to get an idea, so it 4 is 2 square, right? It will 2 raised to 38. And just to give you an hint, I mean 2 raised to 10 is like 1024, right? So this is like a very big number, a really big number. So it's 2 raised to 30 will be like 10. So approximately this is 10 cube. 10 cube raised to 3, right? This will be 10 raised to 9. I mean, even bigger than this. So it's a very big number. So it's much less than 1, right? So it's like approximately 0. So it is going to be a very small quantity. So from the given options, the first option is saying that value of, so we are obviously calculating the norm of it. So the value of nabla is close to 0. So that is the correct option, right? I mean, that is correct. So value of nabla is close to 0. So that will be the correct option. All right. Let me know if I was not clear at any point or something was not clear. Okay. Okay. So fourth is done. Let's see the sixth question. Okay. Sixth question is related to.
Hi, just for with respect to the sixth question, I'd like to point out that the answer according to what is given in the slides is B, but what is
B.
mentioned here is C. So if you can also please clarify that. The answer here is C, so that's why according to the slides it's B. So was the slide wrong? Solution is wrong?
Uh, yeah. So maybe okay. Okay, let me take that question. So let me see what are the other questions. Sixth one is there and last is eighth, right? What is the eighth question? Eighth question. So let me just explain the eighth question. It's very easy. After that, I will explain the sixth question as you have some doubt related to it. Okay. Let me take the eighth question first. I hope that's fine, right? If there is no issue. Like eighth question will be done in some 2 minutes. So eighth question is saying what is the loss function if, in the RNA, right? So loss function L for an RNA. Do you have any question? Okay. All right. So I don't know, Mona, you are unmuted. Do you have some question?
No, no, it was eighth. Eighth is not loss function. It is which type of neural network is best suited for processing sequential.
That
Loss
is the
function
10th
is
question
ninth.
that I can see. Oh, I don't know. Is there some mismatch of because in on my screen it is showing that it is the eighth
Okay, I
question.
have actually the solution printout. I have not opened the assignment. I'll check the assignment. The
Okay, okay.
now
So can you tell me the question?
it is which type of neural network is best suited for processing sequential data, and the four options are CNN, RNN, FCN, and DBN. And in fact,
Yeah.
I had a problem in ninth also. Sorry, I didn't mention that earlier.
Okay. So the 10th question is saying which type of neural network is best suited for processing sequential data? Well, this is a very straightforward question, right? I mean, sequential data, as we have been discussing. So there are what four options. Let us see each of them one by one.
So
First
actually,
is
the thing
CNN.
is, what they have done is in eight also. Why I got confused was in the answer they have written C, and they have in the words they have written RNN. I know it's RNN, so
Oh,
that's why the
I see.
confusion is there. They have ticked it as
Yeah.
C, fully connected neural network, and in the words they have written RNN.
Oh, I see. I see. Okay, so there might be some printing mistake from their side, perhaps. Yeah.
The answer should be RNN, right?
Yeah. CNN isn't the correct option, as you all know.
Yeah, yeah.
I mean, it is used to, work deal with spatial data. RNN is the correct option. We have been seeing that. Okay. FCN, fully connected neural network, cannot deal with sequential data. It can only deal with a vector input. So that is also not a correct option. And deep belief network is something that you have not been taught, but deep belief networks is something that is probabilistic, and that also doesn't work with sequential data. So that is not a correct option either. Okay, uh, so I hope this is fine, right? If you want me to explain, you can let me know. But I think it's a very straightforward question. Okay, so I think you said eighth is not required. So I am crossing eighth question. Okay. 10th question you said. 10th question is also done. I hope only question that is remaining is sixth, right?
Yeah,
Or
six
is
and
there an
nine. Why is nine sum of cross entropy? Because each one of them have to be taken.
yeah,
It's
yeah.
not
So
cross entropy,
as
sum of cross
so,
entropy.
so as I was saying here, right? So where do we go? Yeah. So the loss function that we discussed here, right? This thing, right? So I mean, so let's say, I mean, there is some prediction kind of. So, I mean, generally RNNs are used in you have to predict something at each time step, right? So each of them L1, L2, and till Lm, each of them will be cross entropy. So your entire loss function is sum of cross entropies. That is what is meant by sum of cross entropy. So what was your doubt? Like there some confusion or something?
Yeah, okay, fine. It's clear. It was very trivial actually.
Yeah. All right. So moving to the question that you're saying, which one? Sixth question. Where did it go? Right. So sixth one is what we have been worrying about. Right. So let me explain it. And let me also say that you can actually fight with the instructor with the answer, but I will tell you my honest opinion. What it is. Okay. Okay. So here is the thing. So LSTMs. Maybe I will use the same notations as it was used in the uh, lecture slides. Okay. So the LSTMs. I mean, I won't explain it in depth. I hope you have already seen the lectures. However, this is how it goes, right? Okay. Uh, so there are two ways to look at this question. Okay, so let me give you the and each of these ways will give you two different answers, honestly speaking. Okay, so let me explain the first way, which I think you mentioned, right, that first will be selective write, then selective read and selective forget. I think what was that option,
Yes,
first
B
option, I think.
option. Yes, B option.
Yeah, B option. So let me tell you how that answer will come. Okay, so this is the sixth. Okay, this is the sixth question. Maybe you will use separate colors for the two cases. Okay, so this is case one. So the one way to look at this is the following. Okay, so there is some st minus one, that so the hidden representation from the previous layer, st minus one is coming out. Okay, maybe I should use a vector to represent it. Some st minus 1, this is a vector. You do a dot product of it with your uh, what do you call it, uh, forget gate, I suppose, right? So you use some ot minus 1 to forget, or not forget this input. Okay, and you get something as output, that you pass and use sigmoid to. So there will be some xt that is there. Let's see, some xt that you will forward. So and you like multiply this with w, multiply this with u, and take the sigmoid, like similarly as we have been doing it, and the output, whatever it is, right? You call it, let's say, st tilde, and you use this to multiply it with something, another vector, which is it. Okay, and you add whatever the previous gates was. Okay, so st minus 1, let me st minus 1. Okay, so I'm short of. Okay, let me see, I can do something. Uh, yeah, I think this should be st minus 1, and use something, another gate, ft, to do some dot matrix. So this is what the general architecture of LSTM is. And on top of that, this operation is what we call selective write. Selective write. Right? This operation is what we call as selective read. Selective read. And this operation is what we call as selective forget. Okay. So this is the notation that is being used in the lecture slides. Okay, I'm just picking it from there. So if you look at LSTMs from this perspective, all right, you will see that what is the first operation that is being happened. Like the first thing that you are seeing is that from the previous layer, some the hidden, the activation from the previous uh, layer comes in st minus 1, and you apply the selective write operation. So this is the first step. Okay, then calculate the sigmoid function from your the current input, and you do this whatever you get st tilde, and multiply it with some it, and this you do this operation, which is selective read. This is the second option. And the third operation that you are doing is you are taking again this st minus 1 that was here to and multiplying it with some another gate, which is ft, and we are saying this is the selective for. So this is the third operation that is there. If you look at it from this way, the sequence is what? The first thing that you do is selective write, uh, selective write, right? And then you are doing selective read, and then we are doing selective forget. Right? This is the sequence, right? And this corresponds to your which option? I think this is option right, read and forget. This is the option D. Okay. However, let me also show you the other case. Okay. Other case is that you took case. So let me call it case two. Okay. And the case two looks something like this, right? What I will do is I will start. You know, I will do the following thing. Okay. So I'm saying that okay, something from previous layer comes in st minus 1. So I am thinking of it from the current perspective, right? So the current model just sees something from behind that is coming, which is st minus 1. Okay, I am multiplying that with w. The current input, whatever it is, let's say xt, that is going here, and we are calculating the sigmoid. Then whatever the output is, sorry, whatever the output is, which is let's say st tilde, I am doing the dot product of it with something called IT, right? And I am also taking whatever the previous network's output was st minus 1, right? And I am doing a dot product with what ft, okay, okay, right? Okay, done into the same issue. Let me resize. Okay, great. Okay, right. So this will I will get something out of it, right? So what I will get is, uh, you know, so this is what I will get. So output of the output of these operations will give me something called ST, right? And now what I am doing is, I am doing ST a dot product of it with respect with some another gate OT, right? And this is, this whatever this operation is, I will forward to the next model at the next time step. Okay, this is like your HT. So this will give you your HT, and HT will go on for. So HT will again come something like this, and something like that. Anyways, so this is again this is your selective write operation. This is your selective forget, and this operation is what selective write. Selective. Sorry. Okay, this was. Sorry. This was selective read. Right? This was a selective. Right. This is the operation. Okay. So from this perspective, what is happening first is, you are getting some input from the previous model, st minus 1. You are using the current input xt, and you are calculating this st tilde, which is this vector. You are using this gate it to calculate, perform this selective read operation. You are also using the previous networks, previous time steps activation st minus 1 to, calculate the selective forget operation. Whatever your output is, let's say some st, you are using ot to perform the selective write operation. So from this perspective, what is the first operation that you do? This is the first operation, this is the second operation, and this is the third operation, right? So the sequence is what? This sequence is selective read, then selective forget, and then selective write. This is the sequence, right? From this perspective. So according to now, so this sequence corresponds to your option, which is this option, read, forget, and write. Read, forget, and write. This is C option. Yeah. So this corresponds to your C option. Yeah. So it's the matter of how you are looking at your operations, right? So it's the matter of how you are looking at the operation. So if you look at it, from this perspective, the B option is correct. If you look at it from this perspective, the C option is correct. So am I clear? Maybe was I clear? Was I able to explain the difference between the two operations? It's just cyclic, like so what I mean to say is basically this, right? So the So if I use some shorthand notation, what we are seeing here is that you are doing first read, forget, write, okay. Then again you will do the same operation, read, forget, write, read, forget, write, okay. However, one can also see this operation in the following way, right? That someone can say that, okay, well, I will look, write, read, and forget. Okay, write, read, and forget. Something like this will happen, right? This is how I think this is where the issue is coming, right? You can look at it like read, write, forget, read, forget, write, read, forget, write. This operation. You can also look at it in this way. Okay, so from this angle, it looks that both of the options would be correct. However, the reason that this C option is more correct, I will explain, is perhaps because uh, think of it from the first. Think of, so this is the model that we drew. Yeah. So this so think of the model from the first time step, right? This was the first time step, right? From in the first time step, there was no previous model here, right? So there was no st minus 1 and st minus 1. What we do here is, there is some h naught that we give, and h naught is again a learnable parameter, and we do that thing. So if you start from the look it from the first time step one, okay, first time step, there is no this operation. What was it called? There is no selective write operation that is happening, right? From if you look at it from the first time step perspective, this operation is not happening. All we are doing is here we will give some x naught here, and it will go here, and xt minus 1 will go here, and stuff will start. So the first operation that will happen is what? The first operation that will happen is this read operation. Then we will do this forget operation, and then we will do the selective write operation. Because of that flow, perhaps this option C is more correct than option B. Okay, is that clear? I don't know if I was able to explain. Okay, all right. So someone has said that asked to explain question two. Question two. Okay, so let us go again back to the third question that we did. Something here. All right. So the second question is saying we have trained the above given RN, this model that I drew earlier, this model, and it has learned weights and biases accordingly. If the weights of x1 to h1, x1 to h1, this weight, right? If this weight is at s5 is given to be 2, okay, what will be the weight at s6, the sixth time instant? Well, as I explained, right? So the model is it is said that the model is already trained. Okay, the model is trained, so model is fixed. Okay, if the model is fixed, what does it mean? It means that this M, which is which is nothing but this network, is fixed. Okay, if this is fixed, it means that eventually, if I have fixed this network, these weights are not going to change. Okay, it doesn't matter at what time instant I am talking. Okay, so if this weight is 2 at S5, it will be 2 at S6 as well. That is the whole point of using recurrent networks, that you are using the same model again and again. Hence, the value of the weights won't change with time step. It will remain the same. Is this clear? So the answer will be 2 itself. It won't change. So is that clear, Jyoti? Uh, I don't know. So I just briefly explained it because it felt that it was simple. Maybe, but if it's not, you can. Okay. All right. So maybe I will end it here. Let me know if I was not clear, or if there is some doubt that is still there. Uh, if not, then we can end this session. Let me know from the comments, or you can unmute yourself and say. All right. All right. Thank you for joining this session. right? Thank you for joining. I think this was our this is perhaps the second last problem solving session. We will have one more problem solving session, which will be around I think next week, yeah. And after that, I think you have some exams. So best of luck. Let's meet next week. And yeah, thank you. Thank you for joining. Have a nice evening. See you next week. Yeah. Okay.